All right, Titans. In my last lesson, I gave you an introduction into trigonometry, how we can identify the opposite and adjacent and hypotenuse in a triangle, how we can identify what to use, sine, cosine, or tangent, what those even mean, sine, cosine, and tangent. Now I want to go through an analysis or a type of problem that we will be doing very often in physics. In physics, it's very common to be given a vector. Now, there are two kinds of numbers in math, vectors and scalars. Scalars, S-C-A-L-A-R-S, a scalar is a number that has a magnitude only. If I tell you my mass is 65 kilograms, that's how much matter is in me. There's no direction to that. If I tell you the temperature in this room right now is 72 degrees, that's a scalar quantity. It has a size, 72 degrees. It doesn't have a direction. I wouldn't say, oh, it's 72 degrees in here to the west. I mean, that makes no sense. The other kinds of numbers are vectors. A vector has magnitude and direction. A vector has magnitude and direction. You might recall the criminal vector in Despicable Me does crimes with magnitude and direction. The magnitude is the size of the vector. The direction is which way it's pointing. For example, suppose I have a vector that is 15 meters long. In this direction, I'll call that 30 degrees above the horizontal. So a vector is 15 meters at 30 degrees above the horizontal. That might be a displacement vector, how far something moved in this certain direction. Okay. Well, what do we do with that? I mean, it is what it is. It's just a number at an angle. But the thing about physics is that we find it easier to deal with numbers that are straight up and down or straight to side. When somebody gives you an angle vector, it really messes you up. This, by the way, I could draw this as 15 meters. It could be 15 newtons if it was a force vector. Could be 15 miles per hour if it was a velocity vector, or meters per second. Could be 15 meters per second squared as an acceleration vector. It could be 15 Tesla if it's a magnetic field vector. We won't study that this year, but there's lots of different kinds of vectors. But for this displacement vector, what can I do with that? If I don't like angles, I like vertical, I like horizontal. So what I'm going to do is I'm going to take this vector and I'm going to turn it into a triangle. I'm just going to simply draw a vertical line and a horizontal line and make that a triangle so that my vector is now the hypotenuse of my triangle. And I'm saying I want to find the vertical and the horizontal. I'm going to call the vertical y and the horizontal x. I think that's reasonable. So could I do some trig here to find out what x and y are? Well, x is the adjacent side. We learned that in my last lesson. So the adjacent side. Hypotenuse is my 15 meters. A and h, if you check your notes to remember what a and h are, I think you'll find that a and h is a cosine problem. So I can write an equation. I can say cosine theta is adjacent over hypotenuse. And I should really use that concept to deal with how would I find x given this. And again, my goal is to find out my horizontal and my vertical instead of this awkward angle piece. So how do I find x, the adjacent? Well, the adjacency x, so I want to solve for a. I'm going to do that by multiplying by h. And now I can say a equals h cosine theta. So for this particular problem, that equation, a equals h cosine theta, will tell me how to find the adjacent side. I want to make this a little more generic, though. The hypotenuse is my 15-meter vector, right? So could I generically just say that my hypotenuse is the vector itself, v for vector, times the cosine of angle? And this is when the adjacent is right here. I'm calling that x in this problem. So I could actually write x equals v cosine theta, couldn't I? In fact, I'm going to put a box around that because that is really nice to know. It's not on the equation sheet, but it comes from simple trigonometry based on this triangle. And it tells me that if I have a vector measure from the horizontal, which is what we typically do, I can find the horizontal component by saying v cosine theta. Okay. What if I want the y? Well, the y is the opposite. I know my hypotenuse. So O and H, that makes sine, I think. So I could write sine theta equals opposite over hypotenuse. I'm going to do something kind of similar right here. I'm going to say, I want to find out the y, that is the opposite side here. Well, to get opposite by itself, I have to multiply by H. And I can say O equals H sine theta. Or in this application, the opposite is really the y. The hypotenuse is actually the vector times the sine of the angle. That too is worth a box. It comes from simple trigonometry, understanding what the concept of sine means. But I can generically say that if I have a vector measured from the horizontal, if I need the x, I do v cosine theta. If I need the y, I need v sine theta. It's kind of convenient. I'll tell you the way I usually do this. Quick shortcut. Notice if your vector is always the long side, true? The long side is the hypotenuse. So the hypotenuse is going to be part of my trig function. Well, which functions have hypotenuse? Sine and cosine. Tangent does not. So I'm never going to use tangent when I'm trying to break a vector down into components. I'm never going to use tangent. It's always sine and cosine. So now that makes my problem a little bit easier. In this problem, if I'm trying to find the adjacent, I just think, oh, adjacent and hypotenuse, A and H, that's cosine. This must be V cosine theta. This one, that's the opposite, O and H, that's sine. This must be V sine theta. I know that might sound a little strange to you that I was just able to do that in my head, but as time goes by, I think you'll get to the point where you can recognize that. In the meantime, it's good to have these notes and be able to look at these notes and refresh your memory about how we came up with this and how we came up with this. I never finished my calculations. Let's do so. In this problem, my x is the vector, that's 15 meters, times a cosine of theta. Theta is 30 degrees. So I fill in my cosine 30. 15 meters times a cosine of 30. Grab a calculator here. 15 times cosine of 30. I have 12.99. I'm going to call that 13 meters. And how about over here? So this is 13 meters for my x. How about over here? I can say y is v sine theta. The vector was 15 meters long times a sine of 30. Sine of 30 is 0.5. 0.5 times 15 is 7.5 meters. Oh, wait a minute. If the vertical of y is 7.5 meters and the horizontal is 13, how can I say 15 is 13 and 7.5? Those 13 plus 7.5 is 20.5. That does not give me 15. Did I screw something up? No, because we know the three sides of a triangle do not add up. They add up as using the Pythagorean theorem. So if I do 13 squared plus 7.5 squared, bet you it's 15 squared. Try it, and I think you'll find it works. So here is a sample type of problem. We're going to use this a lot of times this year, but you should be able to, from a vector, from a triangle, from a vector, be able to draw triangles, horizontal and vertical, to see that vector, and then figure out what the x and the y are going to be. Now, your vector might be going up this way, in which case you drop down a vertical and a horizontal. Your vector might start out going downish, in which case you have a y that's negative and an x that's positive. So you can draw it all sorts of different ways. Don't worry about that. Just practice and practice, and you'll be good. Hopefully that helps. Have a great day, Titans.